So for number 1 you have 25 centimeter cubed and 0.20 moles of NaCl. You also have 75 centimeter cubed of 0.020 moles of CaCl, and you need actually CaCl2, and you need to calculate the concentration of Cl minus. So because no reaction takes place, you can just use the equation C equals N over V. V is already given. You need to calculate N to get the concentration. The equation for NaCl is Na plus with Cl minus gives you NaCl, and the ratio is 1 to 1 to 1. So you can just use the given and calculate the number of moles for NaCl, and you'll get the number of moles for Cl minus in NaCl. The equation is N equals C times V. C is 25 from centimeter cube to meter cube times 10 to the power of minus 3 times V, which is 0.2, and you will get 5 times 10 to the power of minus 3 moles. Now the equation for Ca is Ca with 2Cl gives you CaCl2. The ratio is 1 to 2 to 1. So you can calculate the number of moles of CaCl2, multiply it by 2, and then you'll get the number of moles for Cl. So the equation is N equals 2 times C times V, which is 2 times 75 centimeter cube to meter cube times 10 to the power of minus 3 times V, which is 0.020, and you'll get 3 times 10 to the power of minus 3. So the number of Cl minus in total is 3 times 10 to the power of minus 3 plus 5 times 10 to the power of minus 3, which is 8 times 10 to the power of minus 3. And so we said at the beginning that the equation is C equals N over V. V is already given, 25 75 times 10 to the power of minus 3, because from centimeter cubed to meter cubed, and the total number of moles for the Cl minus is 8 times 10 to the power of minus 3. Using that you'll get 8 times 10 to the minus 2 molar.
A solution is formed by mixing 1.0 liters and 1.0 molar of KCl to 1.0 liter and 1.0 molar of PbNO32. Part A says, calculate the mass of PbCl2 that will form assuming complete precipitation. Okay, so first we write the given, which is concentration of KCl is 1.0 molar, with the volume being equal to 1 liter. And now for PbNO32. Our required to find is the mass of PbCl2. Okay, so first we need to find the number of moles of everything. Okay, first we start off with the number of moles of KCl, when the formula N is equal to Cv. Concentration is 1.0 multiplied by 1.0, which gives us 1 mole. And now for the number of moles of PbNO32, which is Cv, which is 1.0 multiplied by 1.0, which is equal to 1 mole. Okay, for the concentration of, for the number of moles of K plus, it's 1 mole. And the number of moles of Cl minus is also 1 mole. And then the number of moles of Pb2 plus is 1 mole. And the number of moles of NO3 minus is 2 moles. total volume is equal to 1 liter plus 1 liter, which gives you 2 liters. Okay, and now let's also find the concentration of NO3 minus, which is N over V, which is 2.0 over 2 liters, which is 1.0 molar. And now for the concentration of K+, which is 1.0 moles over 2.0 liters, which will give us 0.5 molar. Now, let's work on finding the limiting reagent. Let's write down the equation. Pb2 plus aqueous plus 2Cl minus aqueous gives PbCl2 solid. Let's write the number of moles for each, 1 mole and 1 mole, and then we divide by the coefficient. Here the coefficient is 1, so we divide by 1, and here it's 2, which gives us 1 and 0.5. And obviously 0.5 is less than 1, so Cl minus is the limiting reagent. Now let's find the number of moles of the excess reagent, which is Pb2 plus, which is 1 minus 0.5, which is 0.5 moles. And now let's find the concentration of Pb2 plus, which is 0.5 over 2.0, which is 0.25 molar. And the concentration of Cl minus is negligible since it is consumed and it is the limiting reagent. Okay, now let's start with finding the mass of PbCl2. Okay, aqueous gives us PbCl2 solid. Let's start by writing the given. So there is 1 mole, and the molar mass of PbCl2 is 278. And we have also 0.5 moles of Cl minus, and this is required to find, which gives us the mass of PbCl2 to be 139 grams, or 1.4 times 10 to the 2 grams. Now, for part B, list the ions remaining in solution in the order of decreasing concentration. Okay, so we already got the concentration of K+, which is 0.50 molar, and the concentration of NO3 minus, which is 1.0 molar. Now let's find the concentration of Pb2 plus. Okay, so from the last question we got that the number of moles of Pb2 plus is 0.5 over the total volume, which is 2 liters, which gives us 0.25 molar. And now let's list them all in decreasing order, the highest being NO3 minus, followed by K+, followed by Pb2 plus, followed by Cl minus, and that's it.
Let's do number 3 now. What volume of 0.50 molar HCl is needed to neutralize exactly 20 centimeter cubed of a 0.020 molar of CaOH2 solution? I'll give you guys a few seconds and you guys can solve it. Okay, let's solve it together. Let's first write the equation that's going on. So we have CaOH2 plus HCl to give CaCl2 plus H2O. Is this balanced? Definitely not. So we have to put a 2 here, and then you have to put a 2 here as well. Now this is balanced. We have 1 mole here, like I'm taking the coefficients here, and 2 mole here. Now we have the number of moles, I'm using stoichiometry right here, of CaOH2, number of moles of HCl. Cross multiply, what you get is n number of moles of HCl is equal to twice the number of moles of CaOH2. All I've done is cross multiply. So now we finally get into substituting. N is equal to Cv, so Cv HCl is equal to 2Cv of, let me just put the 2, I forgot the 2 here, of CaOH2, right? Now the concentration is 0.5, V equals 2 into 0.020 into 0.020 again, and the volume should be equal to 0.0016 decimeter cubed, because what I've done is I've converted 20 into 0.020. And now let's go to number 4. Flasks 1 and 2 are each filled with a different gas and connected to each other with a tap, preventing the mixing of gases. Pressure in flask 1 is P1 and pressure in flask 2 is P2. The tap is open, the gases are allowed to freely mix for some time until equilibrium is reached, and total pressure is measured as P total. Let me just call this A, B, C. Solve parts A to C. And this is flask 2. Let's solve it together. A says find the new pressure of the gas previously in the flask 1 after mixing. Now you should realize one thing, that I have not added more gas. All I've done is increase the volume. I've in fact doubled the volume, 2 times V, right? So since they're inversely proportional, pressure and volume, isn't P1, P of flask 1, new, is equal to P1 old over 2. Because you've doubled the volume, so you have to half the pressure. Same goes for part B, you're doubling the volume. So P2 new, pressure in flask 2 new, is equal to pressure to old, or just pressure 1 old over 2. And C is easy, find the total pressure. All I have to do is P total equals P1 new plus P2 new P1 over 2 plus P2 over 2, and that's it. Let's move on to number 5. I've split the question in 2 parts, parts A and B, and then the second part will have part C. Let's do the first part. 5 says, in the first of 2 experiments, a student is assigned the task of determining the number of moles of water in 1 mole of MgCl2.xH2O. The student collects the data shown below. We have 5 measurements. And then part A says, explain why the student can correctly conclude that the hydrate was heated a sufficient number of times in the experiment. B says, use the data above to 1, calculate the total number of moles lost, water moles. Part B, I says, determine the formula of the hydrated compound. And triple I says, a different student spills some of the hydrate before heating the solid in a covered crucible. This loss will have what effect on the calculated mass of the water lost by the hydrate? Justify your answer. So I want you guys to do parts A and B, and then we'll check them in a few seconds. Let's do part A first. So why can we explain, how can the student correctly conclude that the hydrate was heated a sufficient number of times? As you can see, in the first initial mass is 24 grams. When you heated it the first time, you lost around 1 gram because now some water has evaporated. Second time, you've lost a little more mass, but the third time, you've barely lost any mass. That means basically no additional mass was lost in the third heating, which leads to all water of hydration had been driven off or had been evaporated, because the change of mass is what, 0.001 grams. That's nothing. So basically no additional mass was lost during the third heating. That's why you can say all water of hydration had been driven off or evaporated. And that's the part A. Now moving on to part B, it says use the data above to calculate the total number of moles lost when the sample was heated. So now if you can just see what the mass, the initial mass initial is 24.086 grams, right? Mass final after losing water is 23.162 grams. What's the difference of mass lost? The mass lost, ML, is MF minus MI, which gives us 0.924 grams. So we can say that 0.924 grams of water had been evaporated. They want moles, so we divide by the molar mass, which is 18, which gives us around 0.0513 moles of water. Always take care of significant figures. We have 3 significant figures, that's why we use 3. I. Determine the formula of the hydrated compound. So now we know that 23.162 grams is the mass of the anhydrous, because now that the water is gone, it's called anhydrous. Hydrous means with water, anhydrous means the water is gone. MgCl2 and the container. There's a container plus flask, you could say. Now what's the mass of the flask? Mass of the flask or empty container is equal to 22.347 grams. How do you get the mass of anhydrous MgCl2 only? Well, you should obviously know that it's M initial, or the whole, M final, sorry, because the water shouldn't be there, minus the M flask. And you should get an answer of 0.815. Basically what's going on is, here is you have a container, you had some MgCl2 and water mixed. I evaporated the water and the mass that's total left behind after the water is M final. Now the mass of the empty container is M flask. So if I want the mass of the MgCl2, I have to do this mass minus this mass, right? So now I have this many grams left. Now number of moles of that would be 0.815 over 95, which is the molar mass, 0.00858 moles. But this is not the complete formula of the whole thing, because remember it was MgCl2 dot X H2O, right? So now if we continue, well, to find that X, all you have to do is divide the number of moles of water over the number of moles of MgCl2. Excuse me. Because we have to find a relationship between the number of moles. So it is 0.0513 over 0.00858, which rounds to approximately 6, because we want a whole number if preferable. So 6 is the answer we got was extremely close to 6. That's why we take it to 6. So the final formula for the compound is MgCl2 dot 6H2O. So we find the number of moles of MgCl2. Then to get the X, we do number of moles of water over the number of moles of MgCl2. Coming to part III, the last III part. A different student spilled some of the hydrate before heating the solid in a crucible. This loss will have what effect on the calculated mass of the water lost by the hydrate. Justify your answer. Well, when you lose some of the hydrous HCl, MgCl2 is MgCl2 dot 6H2O currently, right? Some student who was not handling it properly lost some of it outside. Now we have less left. Do you think we only lost H2O in that? No, right? We lost MgCl2 and we lost H2O. But in our calculations, all we've assumed is we're only losing H2O. We haven't, taken into consideration that MgCl2 was also lost in this, based on what we've been doing so far. So, the mass of water lost after evaporation, because we are checking how much was lost, or after being driven off, will be too large. Let me just clarify here, calculated mass, because we will assume that only H2O was lost, when in reality MgCl2 was also lost. That is why the calculated mass of water lost after being driven off will be too large, because we will have no way of knowing how much MgCl2 was lost when that student carelessly lost some of the solution. Let's do part C now. In a second experiment, another student is given 1.47 grams of a mixture containing anhydrous MgCl2 and KNO3. To determine the percentage by mass of MgCl2 in the mixture, the student uses excess AgNO3 to precipitate the chloride ion. Do parts I and II, and I'll wait for a few seconds. Okay, let's do it together. Part I asks us, starting with the 1.47 gram sample of the mixture dissolved in the water, briefly describe the steps necessary to quantitatively determine the mass of the AgCl precipitate. To help us, let's use an equation of what's happening. So AgNO3 we're adding. I'm just going to use the states to help me understand better. Plus, let's see, MgCl2 to give AgCl plus MgNO3 we do this thing and then the outside, right? NO3 and to balance 2, right? This is going to be a solid and this is going to be aqueous. So what's happening is we're precipitating this, right? So the first step has to be obviously to add excess AgNO3. The reason why we're adding excess AgNO3 is because we have to make sure that every single mole of MgCl2 is being cancelled, is being used up. That's why I have to add excess. So we have to keep adding until there's no more precipitate being formed. Then number 2, we filter the solution and we separate the AgCl, which is the precipitate. Number 3, we wash and dry the AgCl to make sure there's no water left over, so we know the mass exactly. And then part 4, we determine the mass, either by weighing the precipitate or just by subtracting the mass of the total before minus the current mass, and whatever is gone is the mass of AgCl. Going to part II now. There's 2 parts in II, so I'll just call them part 1 and part 2. Part 1 asks us what's the number of moles of MgCl2 in the original mixture. Let's go back to our initial equation, which said MgCl2 plus 2 AgNO3 to give 2 AgCl plus MgNO3 right? So what we're supposed to do is we have to find the number of moles of MgCl2. Well, isn't the relationship between MgCl2 and AgCl 1 to 2? So isn't this equal to number of moles of AgCl over 2? Well, since we don't have the number of moles of AgCl, it's mass of AgCl over molar mass of AgCl, right? Because number of moles is mass over molar mass, right? Now, since we had the mass of the precipitate, it was given in the second part to be 2.74, and we can easily get the molar mass, which is 143.32, all of that over 2. We should get the final answer in number of moles to be 0.00956 moles. And we have answered the first part of part II. So what we did was, we did the ratio, it was 1 to 2, so it's this over 2, and then mass over molar mass, we can easily get that, and then we got the number of moles of MgCl2. Now going to the second part, where they asked us the percentage of mass of MgCl2 in the original mixture. We have N of MgCl2, it's 0.00956 moles. We can easily get the mass, it's number of moles times molar mass, which is 95.2, which is the molar mass, times this thing, which gives us 0.910 grams of MgCl2. Percentage is obviously 0.910 over the weight of the whole thing, or the mass of the whole thing, which is 1.47 grams, the sample. You do times 100% and you should get 61.9% MgCl2 by mass. So the mass of MgCl2 is 61.9% of the mass of the complete sample. Start part number 6 now. A rigid 8.2 liter flask contains a mixture of 2.50 mole of H2 and 0.5 mole of chlorine and sufficient argon so that the partial pressure of argon in the flask is 2 atmosphere. The temperature is 127 degrees Celsius. Let's do part A now. You guys can solve it for a few seconds before we check together. Let's first state the given. Let's do it together now. We know that the volume is 8.20 liters. We know that NH2 is equal to, let's see, 2.5 moles. For Cl, we have 0.5. We know that the temperature is 127 degrees Celsius or 400 Kelvin. You just have to add 273. And we know that the pressure of argon is 2 atmosphere. We are looking for total pressure. Now, does anyone know what is the equation that relates number of moles, volume and temperature? PV equals nRT, right? And since we're looking for the pressure, it's nRT over V. Now, we don't know what's the volume for the hydrogen. What is it? When you have a container like this that's rigid, any gas, the volume for it is the volume of the entire container, because the gas is within the container, so the volume of each gas is 8.2 liters. So let's see, for P of H2, it's N, which is 2.5, R is 0.082, temperature is 400, all of that over 8.2, and we should get something around exactly 10 atmospheres. Continuing with chlorine, P of Cl2, now the number of moles is 0.5, R is the exact same, and temperature is also the same, volume again being the same, and we should get 2 atmospheres. Let's move on. Now we have the pressure of hydrogen, we have the pressure of Cl2, we have the pressure of argon. Isn't this the whole thing is P total? So 10 plus 2 plus 2, which is very easy, 14 atmospheres. And that's part A complete. Let's do part B now. Part B says calculate the mole fraction of H2 in the flask. Mole fraction of anything. So mole fraction is X with the gas represented as Y. That's the number of moles of Y over the total number of moles, and total, let's call it. We have the number of moles of hydrogen. We have it for chlorine. We do not have it for argon. So again using PV equals nRT, but this time n argon is equal to PV over RT, which is the pressure of argon is 2 times 8.2 over 0.082 times 400, and we should get 0.5 moles. Now that we have that, we can easily do x of H2, because they're asking us for the mole fraction of hydrogen, which is 2.5, because that's how many moles of hydrogen we have, over 2.5 plus 0.5 plus 0.5, which is 2.5 over 3.5, giving us an answer of around 0.714. That's the mole fraction of hydrogen. And the last one is part C. I'll read it out. The mixture in the flask is ignited by a spark, and the reaction represented below occurs until one of the reactants is completely consumed. The reaction they're showing us is H2 gas plus Cl2 gas to give 2HCl. It's completely balanced, no need to check for that. So now what you have to do is find the mole fraction of all species at the end of the flask, in the flask at the end of the reaction. Now we know that one of these gases, be it H2 or Cl2, let me use red, will become 0. There will be no more moles left. So now we have to consider 2HCl, right? So now to see which one is going to be used up, we have to see which one is the limiting reagent, right? So we have 2.5 moles of H2, 0.5 moles of Cl2, and if you divide by the coefficients over 1 over 1, this is definitely bigger. So this is the excess reagent, limiting reagent. So we know that Cl2 is going to be completely used up. But how much H2 will be left at the end of the reaction? Well, it's a kind of a not official method, but you can easily do just 2.5 minus 0.5. So 2 moles of H2 will be left. Now the reason why I did this is because they react in a 1-to-1 ratio. For every H2, for every Cl2 mole gone, there will be an H2 mole gone. So 2 moles of H2 will remain. So now if we use some easy stoichiometry, if we know that 1 mole of Cl2 produces 2 moles of HCl, how many moles will 0.5 moles produce? 1 mole. So we have 1 mole of HCl produced. And since argon is inreactive, then we have 0.5 moles of argon. Continuing on the next page, now we can easily find x of H2, x of HCl, and x of argon. Very easily. 2 over 3.5, as is the total. This is 1 over 3.5, and this is 0.5 over 3.5. The number of moles of the gas over the total number of moles. And you should get for this 0.571. For HCl, you should get 0.286. And for argon, you should get 0.143. And what's the last gas that is remaining? 0. X of Cl2 is very obviously 0 because there's no moles of gas left of Cl2. And that's number 6 solved. Move on to question 7. 5 identical balloons contain each of the following gases: C2H6, SO2, O2, CO, Ne. Each filled to the same volume at 25 degrees Celsius and 1 atmosphere pressure. Part A says which balloon contains the greatest mass of gas, explain. B says compare the average kinetic energies of the gas molecule, explain again. C says which gas is expected to deviate most from ideal behavior, and D says 6 hours after being filled, all the balloons have decreased in size, predict which balloon will be the smallest. I'll give you guys a few seconds to solve the question and we'll check together. Let's start with part A. Which balloon contains the greatest mass of gas? Now we should pay attention that they have said 5 identical balloons, so the balloons don't affect anything, and they have the same volume at the same temperature and the same pressure. So all of these things do not change anything of the mass. Well, we should know that Avogadro's hypothesis says that when you have equal volumes of gas, same volume, at the same conditions, so same temperature, same pressure, then they have the equal number of moles, right? Now, if you all remember, mass is equal to the number of moles times molar mass. So now what does our mass depend on? If the number of moles are same between all 5 of these gases, it depends on the molar mass. And now if the one with the greatest mass of gas would be the balloon which has the gas with the highest molar mass, and the one which has the highest molar mass is SO2. SO2 has the highest molar mass, you can check that. So part A, the answer is SO2. Part B, compare the average kinetic energies for all the gas molecules in the balloons, explain. Now we should know that the kinetic energy depends on the temperature. If the temperature increases, the average kinetic energy of each gas increases. Since the temperatures are the same, the kinetic energies are the same. So same Ke. Part C, which gas is expected to deviate the most from ideal behavior? Now we should know that as gases get bigger in size and complexity of molecules, they deviate more from ideal gas behavior. What does deviate mean is they act less and less like ideal gases, right? So the assumptions that we have made for ideal gases does not apply to them. So what do we mean by bigger in size? I mean bigger in molar mass. That's how you get bigger in size, right? And we just said in part A which has the highest molar mass, SO2. So SO2 is expected to deviate the most from ideal behavior. Part D now. 6 hours after being filled, all the balloons have decreased in the size. Predict which balloon will be the smallest and explain. Okay. For this one, the answer is neon. So now we have to explain why. Why is it neon? Basically, there's something called Graham's law of effusion, and it is represented something like this. V1 over V2 is equal to the square root of M1 over M2. Well, what we should know is basically the lighter the mass, the quicker it will go. So if mass decreases, the velocity increases. And if you think about it, it makes sense as well. Let's say I have two gases and they are the same temperature, right? Then that means that their kinetic energy is the same. What is the formula for kinetic energy? Half mv squared, right? Now let's say I have two gases. I'll call the first one m1 v1 squared is equal to half m2 v2 squared, right? Now if you think about it, if the mass of the first one is big, then how will the second kinetic energy be the same? Well, the mass cannot compare to the first mass, so the velocity has to be much bigger than the velocity of the first one. So the lighter the gas, the higher the velocity. That's why neon will be the smallest, because most of the gas will be out by that time. Let's move on to question 8. The molecules of a certain gas X of formula NXH2X move 4 times as slow as the molecules of hydrogen gas at the same conditions. Find the molecular formula of X. I'll give you guys a few seconds and you can solve. Let's solve it together. Let's say the given first. So let's say V of H2 is equal to 4 times the velocity of NXH2X. I'm just going to represent them by their formulas. Since the velocities are the same, shouldn't the kinetic energies be the same? Right? Since they are the same temperature, same conditions, right? So since the average kinetic energy depends on the same condition, like depends on the temperature, if the temperature is the same, the kinetic energy is the same. So half m of H2 VH2 squared equals half m and nx, sorry about that, nx H2x. And now I'm just going to substitute by the equation. Isn't this equal to, or no, let's just keep it for now, v and x H2x squared, right? Now if we substitute vh squared, we get half mh2 into 4vx nx H2x squared equals half nx H2x, and then v of all of this squared, right? Now 4 squared is 16. 16 divided by 2 is 8. So 8 times, well, what's the mass of H2? Isn't that 2? 2 V N X H2X, all of this squared is equal to, well, half M N X H2X V N X H2X squared. These two are equal, they cancel. Let's continue on the next page. We had 8 times 2 is equal to half the mass of the unknown gas. Let's call this X. Well, that's 1632. So 32 equals mx, right? Now, since we know that the molar mass is 32 grams per mole, so basically we have nx H2x equals 32. The molar mass of nitrogen is 14, so 14 into x plus 2x, because H is 1. 1 times 2 is 2 equals 32. 18x equals 32. Oh wait, no, sorry, 16x. 16x equals 32. X is equal to 2. And that's the final answer. Let's move on to question 9. Below are two diagrams showing the energy profiles of two reactions. Fill in the blanks under each diagram. Now I want you guys to fill in the blanks. I'll give you guys 2 minutes and then we'll check together. Okay, let's check it together. I'll call this reaction 1, reaction 2. Let's do reaction 1 first. Part A asks us what is the reaction type. So we know there are two reaction types, either exothermic or endothermic. This reaction is, now looking at the graph, we can see that the energy is decreasing. Where is this energy going? Now the energy is being released, right? Because as you all know, energy is always conserved. You cannot destroy energy, nor can you create energy. So this energy hasn't disappeared anywhere. It's gone to the surroundings. And when a reaction releases energy to a surrounding, or when the energy of the products is less than the energy of the reactants, this reaction is known as exothermic. So I'm just going to put exo. Now this reaction obviously releases how many kilojoules? You look at the difference. So this is 150 kilojoules. Blank kilojoules is transferred, blank the surroundings. Again, 150 is released, so 150. Now to or from, to the surroundings. The activation energy of the uncatalyzed reaction is blank, while that of the catalyzed is blank. Now, why do we use a catalyzer? Why do we use it? We use it to lower the activation energy. It gives us an alternate path where the activation energy with catalyst, it has to be less than the activation energy without a catalyst, WC. That's the only reason why it would make sense to get a catalyst, right? So now we have two different reaction paths. We have one reaction path, let me do it in red, that goes like this. And the other one, let me do it in blue, goes like this. Now obviously, just by plain reading, we can see that the red one has a lower activation energy. It goes up a lower amount than going to the final state. So for the uncatalyzed, it's obviously 200 kilojoules. And for the uncatalyzed is 150. Look at the heights here. Now let's move to reaction 2. Now for reaction 2, we can see that the reactants are here, the products are here. Wait, the products have a higher energy than the reactants. So that means it's endothermic. The reaction does not release, it absorbs from the surroundings. Absorbs. How many kilojoules? 75 kilojoules. Why? If you look at the difference, if you draw a line here and here, you see that the height difference is 75. So blank kilojoules is transferred, obviously 75. Is it to or from? From the surroundings. And now again I'm going to use red and blue. This is the red, and let me use green this time. This is the green, which has a lower height, obviously the red one. So the catalyzed reaction would have a lower activation energy, so this would be 200, again looking at the heights, and the uncatalyzed reaction would be 300. So you just look at the heights.
Hello everyone, this is Ali Bihadali and I'm doing questions 10 till 18 of the chemistry periodic revision sheet. So yeah, let's start. A student was assigned the task of determining the molar mass of an unknown gas. The student measured the mass of a sealed 1686 milliliters rigid flask that contained dry air. Now without continuing, to be honest with you, you really don't need to read this. I do not recommend reading it. However, for the sake of revising, I recommend reading it this time, but not in the exam, not to waste time. So read it now so that you don't read it later. Okay? So the only values you need to know so far is this, these two, and these three. Now I'm going to give you some time to solve A, B, and D. I'm showing them on the screen. I'm showing you the question also fully. So I'll give you a few seconds to pause, solve them on your own, take as much time as you need, go as fast as you want, but solve at your pace also. So make sure you solve and do your best, so that when you do a mistake, you would always be able to recall it and possibly fix it next time. So yeah, I'm gonna give you a few seconds to pause if you didn't already. Okay, so let's start. A, what does A say? Calculate the mass in grams of the dry air that was in sealed flask. So we're looking for the mass of the dry air. Now let's just, for now, as a tactic, let's write the symbols of what we're both required to find and given. Let's just write the symbols. We can probably, the formula will probably pop up to us when we do so. So let's do mass. What are we given? Density. I mean, we're not given mass, but as I said earlier, also required to find is considered like, write the symbols, just write the symbols. So density. Now density it immediately gives you the formula. It immediately gives you V, which immediately gives you D over, D equals mass over volume. So mass is density over density times volume. Why did I use mass? Because I said calculate the mass. Now all I did was just blindly use the formula, arrange the formula, and just substitute. So now let's look carefully. Also, I didn't say this at the beginning, but please spare some time looking at the symbols. The units. This might save you future mistakes if you ever do that. So degrees Celsius, torr, this is a special one. Milliliters, possibly something you're gonna change. Grams per liter. Well, yes, you're definitely gonna change that. And we're actually using the volume here and the density there, so we're definitely gonna change. So 1.18 times, we said we're gonna change this to what? To liters, because we're using liters there, and also liters is SI, so that's why you're not changing the other one. Okay, so what happens if you multiply the two of them? If you multiply the two of them, you get, also always check your answer in the calculator, like always do calculations at least twice, or if it's simple calculation, just look at what you have written, just to make sure that you're not doing any mistakes. You should get 1.99 grams. Significant figures, 3, 4, 3. So 3, 4, so 3. Okay, so B, calculate the mass in grams of the sealed flask itself. So we have what? The dry air. We have dry air and sealed. We're looking for sealed. How do we do it? Subtract. So 158.70 minus 1.99, you get 156.71, I believe. Yeah, 1. Anyways, so one remark: when you're subtracting or adding, always compare decimal places. When do you do that? Before the operation. So take it as a rule. Well, it is a rule, I guess. Minus and plus are done before the operation, like before doing the operation. What do you do exactly though? Compare the decimal places. And multiplication, division, do the process after the calculation or after the process. Do the comparison, and it's the significant figures that you compare for the final result to be influenced. So the final result here is not influenced by anything after the calculation. After the calculation, you just write it and that's it. So you always compare the minus, for the minus and plus, you always compare the decimal places first. Once you get the answer, you don't do anything to it. Okay, so say that the 0 is not there, just for the sake of this example. If you don't know what to do, like if you have varying decimal places, before we had the same one, right? But what if we remove the 0? What do we do? In this case, you round this one. It becomes 2.0. You round the one with the more decimal places to be like the one with the least. So like to get the least number of decimal places. So 2, and you subtract. But again, in this case I'm changing given just to show you, so I'm getting it back. Well, we've already done the calculation, so it's right here. Let's remove this so that we have more space. Boom. Let's go. So C, what does C say? Calculate the mass in grams of unknown gas that was added to the sealed flask. So we need unknown. We have unknown and sealed. We have sealed, so of course we can get unknown, right? So 159.45, what the hell am I doing? 45 minus 156.71. Subtract, you should get 2.74 grams. Again, subtraction, same decimal places. I don't care what this is or what value I get here. As long as I care here, I wouldn't care there if subtraction and addition. So part D, using the information above, calculate the value of the molar mass of the unknown gas. Molar mass, that's a symbol, right? Now we just had what? Mass. What other things pop up in your mind? We have the density, I'm probably not gonna use it. We have the volume, we have the pressure, we have the temperature, things are starting to show. Of course, we'd use in this case PV equals N is replaced by M over mass over molar mass, R stays R, and T. So we're looking for molar mass, right? So rearrange the equation. Okay, yeah. So you get MRT over PV. Now time for substitution. We got earlier to be 2.74, so 2.74. R is 0.0. Now, just to avoid confusion, or I mean, I also could be confused, but let me tell you what I know. Do you use 82 or 80? 0.8, I mean 0.082 or 0.080, or a possible other number, maybe the full or 4 decimal place or something. Which one do you use in the exam? Well, let me tell you what I would think. I would honestly believe that they would give you the R in the exam. Why? Because they've done so with the electrons and the mass of the electrons and blah 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 in the physics. In the physics, they give mass of the electrons and the charge of the electron, I believe. At least the mass, or one of them at least. But they give the value that they didn't in the sheet. They only, put it in the answers, but that's it. So I honestly would believe that they would give you the answer, but say that they don't. The answer key uses 80. So for the sake of the example, I'm going to use 80. But one last thing, like for example in the exam they didn't mention, for example, they didn't say which one, and you really want to know if it's 80 or 82, check the other questions in this sheet. If they use 82, probably this is an exception. Like, as in, I don't mean that you use 80 only here. It probably just means don't use 80. Maybe it was a mistake, some kind of thing. Mood, the guy who put the answer. Just, anyways. So yeah, let's just continue. By the way, if I confuse you guys, you can always go back to a few seconds or minutes ago and check what I just said. If you want to hear what I said again, to confirm if you heard it properly, if I missaid something. Also, sorry guys if I make mistakes. I just can't see them immediately. If I see them, I'll correct them. So just don't mind me if I do mistakes. I'll try my best not to do them, not to confuse you. So 750, that's what the pressure, right? Now this is torr. To change from torr to atmosphere, according to the solution, it uses 760, which I honestly did not recall. But now, from now on, to recall them, this looks to me like the millimeter mercury. So that's how we can remember it. It's like the millimeter mercury. So you change by dividing by 760. But then again, this is torr to atmosphere, not millimeter mercury, but just saying that how you could remember it. So what we're left with, volume 1.686. Do the calculation. What do you get? You get 39.0. Now units. First of all, let me tell you significant figures. No, this is you don't care. You take the value, so you don't care. Again, you don't care about this one. And 3 you don't care. 4, so 3. Anyways, so the units. How do you get the unit? Well, what are we doing? We're doing. We're getting molar mass. Well, I know that number of moles is mass over molar mass, correct? So molar mass is mass over number of moles. Unit of mass, grams. Unit of moles, moles. So we are done. Grams per moles. That's part D. So let's use some space here. Okay. Now parts F and E. I'll give you some time to do these because they weren't shown on the screen. So have a few seconds to do them. Okay, so let's start. E. After the experiment was completed, the instructor informed the student blah blah that it was the carbon dioxide. So after all this, all what the student does and the calculation, everything, the teacher decided to tell them that it's carbon dioxide, and it's of course 44 degrees. What degrees? 44 grams per mole, the mole mass of the carbon dioxide. So you do get a different value than the value you've calculated. And which one is wrong? Of course, this one's wrong, but of course, due to some error, which we later on will try to figure out which is what could be possibly the error. But for now, we need to calculate the percentage error. So to do that, it's always calculated minus real or given or whatever it's called, minus over the real given, whatever it's called. So the calculated one minus given over given, or real over real. So anyways, calculated is what? It's 39 minus 44 over 44, and doing this quickly, minus 11.4%. Let me just double check. Also, you multiply by 100 and percent. There you go. 39 minus 44, just to double check the calculation. 11. Okay, correct. So what does this tell you? This tells you that the value we just calculated is less than the value we're supposed to get by an 11.4%. Minus tells you it's less, and this number gives you how much, by how much. So F, we're taking cases. F is saying for each of the following two possible occurrences indicated whether it could have been responsible for the error, or blah blah blah. You need not include any calculations in your answer. So the only thing you need to say is this possible, is it not, and why. So let's look at occurrence 1. The flask was completely flushed with CO2 gas containing some sulfur dioxide impurity. Well, that's basically saying that you had some CO2, but rather than saying only CO2, you had possibly some sulfur dioxide impurity in it. Now, we said some and some impurity, so it's not as much, but you still had it. Now, sulfur dioxide, is it denser or less dense than carbon dioxide? It's denser, right? So, unless, it's a small, incredibly small amount, but it's still denser than CO2. So, it slightly would deviate the molar mass. It would slightly become bigger, a slightly bigger molar mass. So, what did we say? A slightly bigger molar mass. What do we have? A slightly, well, not exactly slightly, but it's less than the one we're supposed to get. So we have a contradiction. So occurrence 1 is not possible at all. It's the opposite. It's supposed to decrease. So if you told me somehow you had nitrogen, which is 28, and carbon dioxide is 44, that's possible. Yes, it is possible. A possible occurrence. Not sure if it chemically wouldn't work, but realistically, with calculations and all that, it would work. So yeah. So occurrence 1 in this case, because they're using SO2, it is impossible. Occurrence 2, the temperature of the air was 23 degrees, but the temperature of CO2 was higher than the reported 23 degrees. So it's basically saying that the temperature that we have, we supposedly are supposed to be given a higher CO2 temperature. So they're telling us that we got a temperature that's less than the real temperature. Wait, let me rewrite it. We got a temperature, that's what we got, right? 23 degrees Celsius, less than what we're supposed to get. So because we got a lesser value, if we go back to the equation down there, if we got a lesser value, what are we supposed to expect to get for the molar mass? A lesser value, right? And what did we actually get? We indeed got a lesser value. So this is in fact consistent with the equation, or at least the relations in the equation. Yeah. So occurrence 2 is plausible. It could happen. And so we don't have anything to say no to it. So occurrence 2 happens, or possibly could be, occurrence 2 could possibly happen. Why? I just said because you can immediately reference the formula. You can say in the formula blah blah blah, that if the temperature increased, in this case decreased. So if the temperature decreased, the molar mass would decrease, which is consistent with the calculated molar mass. You can say this however you want. You can go back to the marking scheme or the given answer, sample answer. Probably said it better than me, but yeah. Anyway, so next question, 11. 6 grams of a gas exerts a pressure of 0.20 atmosphere. What extra mass should be added in order to increase the pressure to 0.80 atmosphere, keeping other variables constant? So what's changing in here? We have the mass is going to change. We're going to add a certain amount of mass, and we have the pressure. The pressure is going to increase in this case. So obviously, if the pressure increases, the mass should increase to increase the pressure. So what relation will we use? We will use this relation, M1 over P1 equals M2 over P2. Now the orientation doesn't matter, which one's up, which one's down, doesn't matter, as long as it's directly proportional, so one over the other, giving a constant. That's how you're equating them. So yeah, so let's continue. So we are looking for the added mass or the extra mass, but before that let's find the final mass first of all. So M2 is P2 over P1 times M1. Okay, so how much is P2? P2 is 0.8 0.20 times M1, which is 6.0. You get 24. Yeah, 24 grams. Two significant figures. So 24 grams. We're looking not for the final mass, we're looking for the added mass. Like realistically, when a person has a certain amount of mass and they want to know how much to add to get this amount of pressure, so they're going to subtract. So 24 minus 6.0 equals 16. Yeah, 18, sorry. 18. Yeah, okay. 18 grams. Just a side note, 0.0, there's no decimal here, so you round this to 6. 24 minus 6 is 18. So if you have any doubts, I hope I cleared it for that part. So B, a fixed mass of gas at 0 degrees Celsius exerted a pressure of 0.2 atmosphere. What will the pressure become if the gas is heated to 27 degrees Celsius at a fixed volume? So the volume is fixed, so we don't really care about it. We have the pressure, we have the temperature, and these two are changing. So pressure and temperature, P1 over T1 equals P2 over T2. Okay, so in that case, by the way, also same thing as that one, the orientation doesn't matter. Okay, so let's continue. We're looking for P2, correct? So P2 equals T2 over T1 times P1. So T2 is what? T2 is, yeah, okay. So T2 is 27, let me just close this, 27 plus 273 over 273 plus 0, so I'm not gonna write it, and the pressure, initial pressure is 0.20. Now just add them, 273 plus 27, yeah, 27 over 273 times 0.2. You get 0.2197, so on. Now you're adding here, I guess you shouldn't really care as much, no, but this one is again two significant figures, so 2 here, same thing, so 2 what? Atmosphere, because you're looking for pressure, and it's pretty much easy. So yeah, okay, so we're doing question 12, but before anything, download the new or the updated revision sheets for the chemistry. I uploaded it on the main group, but you can also download it from your friends or web school. So I'll be giving you a few seconds to pause this video and try solving this question on your own, and once you're done, unpause and we'll do it together. Okay, so let's start. So first of all, before anything, we here are using we're using an iron 2 compound, and we're titrating it with what? With the permanganate ion, with a permanganate solution, but it's not given to us, so I'm just going to mention the ion for now. So let me remind you a bit about titration. So in titration, let me just do this. Okay, so in titration, Here they're just adding the solution that's going to be your main reactant, which is here. In this case, it's the iron 2 solution, or the iron 2 compound. So your solution now needs a titrant. This is called the titrant. You're titrating with this. So this titrant, which in this case includes the permanganate ions, you're dropping it drop by drop, drop by drop, as you can see, drop by drop. So what you're doing is you have a certain concentration here, and you have an incredibly small concentration here, which is its value is a drop. These two will definitely, as you can see, it will definitely react to they will definitely react to give, as you can see, Fe3 plus Mn2 plus some water. So basically the idea is whenever there's a permanganate ion, both the Fe2 plus and the permanganate ion are going to give, and I mean some acid, they're going to give these. So that means any drop that you give is immediately consumed. So with that idea, we're asked, by the way, what I just mentioned is important here, but I'm going to reference it later. So let's first of all do the oxidizing and reducing agent, which is really easy. So the oxygen has, I'm going to go through this quickly, it has a charge of -2. -2 times 4 is -8. So you have x minus 8 equals -1. So x is +7. Now you're going from +7 till from +7 till +2. So that's a 5 decrease. Well, a decrease means it's getting reduced, which means it's the oxidizing agent. Now automatically this is the reducing agent, but if you want to try Fe2 plus into Fe3 plus. 2 to 3 oxidized, therefore it's a reducing agent. We're done with part A. Reasons, well, it says explain using oxidation numbers. Well, I definitely did. I mean, even though I just wrote this, but in the exam you explain it the way I just explained it, you know, like you get the Mn and how much it changed and blah blah. So now part B. The mass of the iron, the mass of a sample of iron 2 compounds carefully measured before the sample is dissolved in distilled water. The resulting solution is acidified with sulfuric acid. The solution is then this is where the H plus came from, titrated with a permanganate ion. So describe the color change that occurs in the flask when the endpoint of the titration has been reached. First of all, let's go back. So as I was saying, you're dropping this drop by drop. So its concentration is really low, and whenever you have a drop, it immediately reacts with the iron 2 ion to give an iron 3 ion and the manganese 2 ion. So with that, what's the color of this? It's greenish. This, it's pinkish. But there's one issue. It's one drop and it immediately reacts. So you'll never be able to see this pinkish color. Well, not exactly, but you won't really see any pinkish color as much. It's going to be mostly greenish. So it's greenish to something. Now let's figure it out together. In titration, you're going to technically neutralize or fully consume one of the reactants. So one of them you have in excess, and one of them is limited. So the one that's in excess is you're going to drop until you see a color change. This is called the what was it called again? The endpoint. It's also called the equivalency point. It's also called, by the way, I really like this one term. It's called the titration error. Now, why is it titration error? Because you're adding one extra drop to see the color, but in between it should be, you can kind of say colorless, because there's no iron and there's no manganese, permanganate ion. Those two kind of like neutralized each other or fully consumed each other. So when you add that extra drop, now you're finally able to see the color change, which is pinkish. That's when you know you have an excess permanganate ion by just one drop. That's how we can calculate the error and all that. So the color change is definitely in this case greenish to pinkish. Greenish due to the Fe2 plus ion, pinkish due to the excess MnO4 or the permanganate ion. So now with that we're done with B. We explained why the color change happens. We explained how, you know, as I said earlier, that this is now in excess before this gets consumed, blah blah blah. Okay, so part C. What effect will adding, let me just do this. Oh, whoops. So what effect will adding more of the what? It says aliquot. Aliquot also refers to here the titrant, which in this case is the permanganate ion. So they're saying, oh, sorry, adding less, yeah. I'm not sure if I said more or less, but here it's saying less. So if you're adding less of the permanganate ion, what will happen to the determined value of the mass percent of the iron in the compound? So you have the iron compound and you want to get the percent mass of iron in its compound. Okay, so with that, it's the mass of the iron over the mass of the compound itself, the Fe2 compound, blah blah. So yeah, so how do you get that? Let's start with step by step to reach this. So first of all, we know that we're doing some kind of neutralization reaction. So with that, you have the number of moles equal. But here, keep in mind the coefficients. You have 5 Fe2 plus, and you have 1 permanganate ion. So for the number of moles to be equal, you multiply this by 5. So as if you're saying 5, 5, you know, for them to be equal. So yeah, so 5 times, or if you want to take it as a rule, it's coefficient times the number of moles. If you have two separate coefficients, you have to take ratios, but let me not go through that. So yeah, the coefficient times the, what are we given? We're given the molarity, and we're given the volume, so we get the number of moles. And number of moles times the coefficient gives us number of moles of what? This is the number of moles of the iron. This is the number of moles of the, let me just write it. Okay, number of moles of what? Of the permanganate ion, MnO4. Anyways, MnO4 minus. So yeah, now you have the number of moles. You want the mass of Fe to reach this. So mass is what? Mass of Fe is, well, we know number of moles is mass over molar mass. We can get the molar mass from the periodic table, but for now let's just keep it M. So mass is number of moles times molar mass. So mass of Fe is what? It's the number of moles times the molar mass. So number of moles we got here, so 5 times molar mass of what? Of the permanganate ion times the volume. Well, I mean, they gave us M and V, so I don't need to point this out. You see, they gave us M and V. So times the molar mass of the Fe, which I believe is somewhere around 55.85 or something. So I'm just going to write it as a number so that you don't get confused if I write, let's say, another M. Yeah. So now you want the percent mass. So how do you do this? Percent mass is simply, as we said, the mass of Fe over the mass of the Fe compound. So mass of Fe, 5, molar mass of the permanganate ion, volume of the permanganate ion, times the molar mass of the Fe itself. Gives us the mass over the mass of the Fe2 plus, I mean Fe compound, Fe2 compound, which is said here to be G. They give us G. So now you truly understand why they gave us M, V, and G. So now we have this equation. So what do? We are looking for less aliquot, so less titrant, so less permanganate ion. Now what does it mean less permanganate ion? Which means less volume, right? So less volume means less number of moles of permanganate ion, which means less number of moles for the iron, which means less mass for the iron, which in fact means less mass percent of the iron. That's how the solution does it at the back. But I personally believe if you have this equation down, you can immediately point out that less volume means less percent mass. But anyways, they're free to do whatever they have, so that's how we do it. Okay, so question 13. Now this one's really easy. I'll give you a few seconds to pause and solve it, and then afterwards we'll do it together. Okay, so let's start. It says 3 grams of ethane were burnt in a calorimeter. So ethane, that's C2H6, and each carbon is 12. So it's 2 times 12 plus 6 equals 30. Now what's that? That's the molar mass, right? So it's grams per mole. Again, if you forgot the units, it's N equals mass over molar mass, and then you know what to do next. So with that, we have the molar mass, we have the mass, so we can get the number of moles. The number of moles is molar mass times, it's the mass over the molar mass. So with that, it's 3 over 30, which is 0.1. Well, if we care about the significant figures in this case, this one's calculated, so it's to 3 significant figures, and we looked for the molar mass, so moles. Now why do we need the number of moles? Why did I do this? Well, we need delta H. the heat of combustion per mole of ethane. Now for that you need minus Q over N. We just got the N, so now you need the Q. For me, I'm going to immediately substitute. The N we said 0.1. Now what for the Q? The Q is, what is Q? Q is MC delta T. However, depends on what C you have, you can do C delta T. The difference is one specific heat capacity and the other is just heat capacity. Here they didn't say specific. Now say that they forgot the word. Look at the units. Kilojoules per coulomb. Now you might say, so this has 2 units. The other one has 3 units. What are you achieving? You're achieving joules, you're achieving energy. So here, to achieve energy, you have to multiply by the temperature, and that's it. So that's why you need only T here. However, here, in the other one, its units must be something like joules, grams per degree Celsius. So, no, sorry, it's down. I knew something was wrong, yeah. So it's per grams degrees Celsius. So that's why in that one you have to multiply by the mass and by the temperature to get the joules. So anyways, we'll use C delta T. We're given C, so 25. And this is 5 degrees rise, by the way, this is delta T. And we have an increase in 5 degrees Celsius, I mean. So if you calculate it, you get minus 1250 kilojoules per mole, which is in significant figures 1.3 times 10 to the power of 3 kilojoules per mole. Kilojoules, because we have here from the C, it's in kilojoules, so we continued with that, and then times 3 to the power of 3, so that we get 3 significant figures. 2 significant figures, because the change in temperature is 2, so we should end up with 2, and that's your answer. Okay, so question 14. I'm showing you part A and B, so pause the video and try your best, and then once you're done, we'll do it together. Okay, so question 14A. We're mixing hydrochloric acid with sodium hydroxide in a coffee cup calorimeter, and we're getting the temperature to be 26 degrees, so that's a 6 degrees change. If you want, let's try that. 6 degrees change. And we're looking for the delta H, so that's immediately delta H equals, well, it's minus Q over N, and then we're going to substitute later. So we have the hydrogen ion, or the H plus OH minus, to give the H2O, water. So assume that the density of the solution is 1 grams. Now this is an interesting unit to use here, because we usually are used to, having volume here, and the trick is that, people keep it in centimeters cubic when you're supposed to change it to decimeter, well, especially when you're doing number of moles and all those standard unit ones. But in this case, when you do Q, now let's do Q. Q is MC delta T. Now this is energy absorbed by the solution. So the energy absorbed by the solution. So in that case, we're talking about a solution. Now solution of what? Of sodium hydroxide, of hydrogen chloride, or is it both? So it's both. So because it's both, you have to add the volumes. Now how do you add the volumes? You add them like this, or do you add them like this? The difference being is that you're adding centimeter cubic here, you're getting the answer to be in the same unit. Here you're adding decimeter cubic and you're getting the answer to be in the same unit, which is again decimeter cubic. So the decision has to be made based on C in this case. C is in what unit? Not C. We're looking for the mass, right? This is all just volume. And to get the mass is density times volume. You can do it by checking density equals mass over volume. You get, mass is density times volume. So you get this. So density, in this case, we have the volume, but we're looking for the units, so we look at the density. Density here has the units grams per centimeters cubic. So you're forced not to change this to be able to get the grams. Otherwise, you're getting something else. So to get the grams, you have to keep the same units. So again, you're going to add them this way. This is the correct way, and this is the wrong way. So add them like this, you get 200. So now we continue. 200, sorry, my bad. 200, that's the volume, times the density, density is 1, times, we said the C. C is what? 4.2, times the delta T, which is 6. So now let's do this first. 200 times 1 times 4.2 times 6. You get 5040 joules. Now N, how do we get N? N, there are multiple ways, but let's see. Okay, so we have volume, we have molarity, we have volume, molarity. Well, we know one famous formula, which is N equals CV. So that gives us now first of all, what do we do? Do we use the hydrochloric, or do we find the H plus moles, which is given from the hydrochloric acids information, which is the volume and the molarity, or the other one, the hydrochloric acid, which gives us the OH, or what do we do? So in this case, we'll look, if you either lock your eye on the water, or let's say the H plus, one of the reactants, you're going to use that and you say per mole of that. In this case, it's 1, 1, 1, 1, so really it doesn't matter which one you pick. Just pick one of them, don't pick both, as in mix or add or anything. So concentration of one of them, I'm going to pick the HCl. So that's 1 times. Now here is the trick, it's number of moles, so you have to change from centimeters cubic to decimeter cubic, because number of moles does not accept anything other than decimeter cubic or liters, somewhere in that scale. So 0.0, blah, 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 you get this, and then you divide them, in this formula. I'm not going to write it, I'm just going to put it in the calculator immediately. 5040 over 0.1. Now you get this big number. So delta H is minus 50400, which is 50.4 times 123 10 to the power of 3 what. Well, we're working with joules, so you can replace this with kilojoules if you want. Kilojoules per mole, and we're done. Now part B, you can do the same thing, so let's just do this faster this time. So we're looking at what? Delta H. So delta H equals, by the way, as I said, I got the coefficients from here, that's why I wrote this here. Now same thing there, this is the reaction, again 1, 1, 1, 1, so I'm going to go really fast, over N, and then we said this is minus MC delta T, over number of moles we said is CV, and the C's are different, keep that in mind, don't cancel. So minus M, mass, we use this from density, so density times volume, times the C, times the delta T, over, we said CV, and then you just replace immediately. I'm just going to show you how you replace, so that you know what numbers I'm using. Again, we're looking at this one, so its density is 1, volume is what? By the way, it's per milliliter, and this is given in liters, so you do the change here also, by the way. So that's 200. C is what? C is this, 4.18. I don't have them. Oh yeah, I do have space, never mind. Okay, so 4.18 times yeah, it's 1.5 change in temperature, and then CV, as I said, pick any of them, it doesn't really matter, they even have the same concentration, same volume, so just pick any of them. And again, number of moles, so you have to keep the units appropriate, so you get this. Let's put this all together in the calculator and see what we get. 200, whoops, did a mistake. Anyways, I'm just going to do this immediately. 200, 4.18, 1.5 divided by 0.2. We get somewhere. I'm not going to double check my answer. It could be wrong, but I'm not going to double check it. I know that the process is correct. So you should get something like this. But just in case, let me just double check quickly. So just to check for the calculation, everything else should be correct, and there you go, it's correct. So we're done from this question. Okay, so question 15. I'll give you some time, pause the video, and afterwards we'll do it together. Okay, so let's do this. First of all, the entire concept is that you have something hot and you have something cold, be it a solution, a solid, whatever it is. The temperature will go from the heat energy is going to flow from the hotter one to the colder one if you have some form of connection between them. In that case, it's direct contact. It's a metal dropped into that calorimeter, which contains water, with cold water to be specific, like from hot to cold. So you're going to have a temperature change. Obviously, the higher temperature one, which is, let's say, the hot one in this case, is going to drop, and the one with the lower temperature is going to increase because it's being given heat energy. Now this will keep happening till they reach a certain level where both temperatures are the same, and you have no net heat change, no net temperature change. So that's, of course, assuming there's no heat loss, there's no energy lost anywhere. In that case, because there's no energy loss here is going to be directly gained here, so that you can equate them. And we know that we're talking about Q's, and Q's are MC, each Q is MC delta T, MC delta T, and M here is the mass of what? The mass of the piece of the metal, for example. Let's have this to be metal, and this to be the water solution, whatever you want to call it. So now the mass of the thing, of the metal. So we have the mass, 20 grams. We have the heat capacity, we want to find that, so let's not put parentheses. Delta T, well, we know for sure it's going to equilibrium condition, equilibrium temperature. So it's going from high 62 to a lower 27.5. Even though the water is 27.5, I just said that the heat change or the temperature change will keep on going until they have the same temperature, which everything is going to stop. No change in temperature is observed, no change in heat energy is observed. After that, after they reach the same temperature, it's like two people fighting, and then when they reach an agreement, everything stops. Same thing here. So you're going to do 62 minus 27.5 equals MC. We have the M to be what? To be 40, and then C is given to be 4.18, and delta T is given to be, well, 27.5 minus the mix, and this minus 25. Okay, so with that you can just C equals, well, let's right now I'm subtracting the temperatures. 26 minus 27.5, you get 34.5. Now I'm multiplying it by the 2, and now I'm multiplying the other side, and then I'll divide by the answer. Mixed two sentences. Anyways, 40 times 4.18 times 27.5 minus 25, and you get the final answer, which is correct, 0.61 if you round. 61 what? Well, this is, well, we're working with this. They even said in, so we really don't care, just immediately joules, grams, degrees Celsius. So that's how we get the answer. Okay, so question 16A and 16B. So pause the video, especially for 16A. 16B you can do it easy, but 16A, you need to know the definition. So try your best, try recalling it. Don't worry, I have a way for you to memorize this easily. I personally use this way. But for now, pause it, try your best, and once you're done, we'll do it together. Okay, so let's do this together. So first of all, we're asked to define the standard enthalpy of formation of a compound. Now, if you want to answer this, you will be kind of like lost. Where do you start? That's the main point. Where do you start? It's like memorizing lyrics of a song. You have to know the beginning and recite it till the end. It's like you remember it sequentially. You know each word, you know the full phrase, you know the full sentence, the full paragraph, from beginnings and endings and stuff. So let me show you this way. I personally use it to memorize this. So for me, I break this into parts. Standard enthalpy formation of a compound. So I break it to standard enthalpy formation of a compound. So here they are. For me, enthalpy means energy change or enthalpy change. Standard means standard states and standard conditions. Formation of a compound, formation of 1 mole of a compound. From where? That's the question. From where? From its elements. So now link all of this together. I know this kind of like looks funny, but let's do this. So it's the formation, it's the enthalpy change. Let's go one by one. It's the enthalpy change of, well, we can't mention standard yet, so let's skip it. It's the enthalpy change of the formation of 1 mole of compound from where? From its elements. In what state? In the standard state, standard conditions. There you go, that's your definition. Let me repeat it one more time if you're not convinced. So, enthalpy change of formation of 1 mole of compound from its elements in standard state, standard conditions. There you have it, you're done. This is personally how I memorize it. So now part B. Let's get this empty space here. So part B, gaseous hydrogen and fluorine combine to form hydrogen fluoride. So let me write the formula, H2 plus F2 to give 2HF. So this is the way it is, but we said 1 mole. So if we're working with, we want the formation, the heat of formation of hydrogen fluoride when talking about the standard enthalpy of formation, which is what we just referenced. We said 1 mole, right? So let's do this 1 mole. So how do we do it? Just write like that, and then you have half. Okay. And then this was, you probably know what to do from now on, honestly, but I'm going to do it anyways. So 540 kilojoules per mole. Oh no, sorry, just 540 kilojoules. And then here you have 1, so you divide by 2. Okay, so minus 2, believe it's just write 4. Okay, so 270 kilojoules, and you're done. That's it, pretty much. Okay, this one's pretty easy. It's also fun. So I'll give you some time. Pause the video and try solving it, and once you're done, we'll do this together. Okay, so let's do this together. We're looking for the delta H of this reaction. We're given 2 reactions. We're asked to use Hess's law. Now this can be really fun. It's just like puzzle solving. So you have Fe2O3. This caught my eye, and here I saw it again. So I'm going to flip this reaction. So let me write. Okay, it's already blushed. So let me flip this reaction. We get Fe2O3 giving 2Fe plus 3 over 2 O2. And here delta H became what? Became plus. So 820 kilojoules. However, we don't just need to do that, we also need to multiply by 2. So let's do that. Here becomes 4, here becomes 6. And this times 2, let me just write it here. It's 1640. 1640. Okay, that's one equation done. Now here, you don't need to reverse, you just need to multiply by 3. That's all you need. So 3 times, 3C plus 3O2 giving 3CO2. Delta H, we need to multiply by 3. So minus 390 times 3, that's minus 1070 kilojoules. And then by Hess's law, in this case, just add. This is 6 over 2, which is 3. 3 and 3 cancel, and you are basically left with 2FeO3 plus 3C. Okay, for a second I thought that was a lone oxygen. Plus 3C to give 4Fe and 3CO2. Delta H, you just add them. Delta H equals, so we have the negative 1170 plus the positive 1640. We get a positive 470. It was an easy one. Okay. Question 18. This is another nice one. Pause the video, try doing your best, and once you're done, we do this together. Okay, so let's start. Question 18. So we're given a formula and we are asked to find the heat of formation, and we're given heat of formation of each one from their elements in standard state, standard conditions. Now we're not given oxygen because it's already in its standard state. You cannot get an element from its standard state if it's already in its standard state. You know, like it's basically saying nothing is happening. So 0. The energy change for this one is 0, the heat of formation. So yeah, so with that, the formula is products, so H delta HF for the reaction is you have the delta HF of the products minus the reactants. So what do we have as products? So it's delta HF of what? Of the products, which we'll start with the CO2, adding the products together, so, and what's the other one? H2O, minus the reactants. We said the O2 is 0, so no need to include it. So I'm gonna skip immediately to the C3H8, and let's just write that. But however, I missed something. There are coefficients right here, because you're forming 1 mole. But do you have 1 mole? Well, for this one, yes, you do, but for the other ones, no. So in this case, it's 3 times the CO2, the delta HF of the CO2, and you have 4 times the delta HF of water minus delta HF of C3H8. There, it's 1 already, so yeah. So 3 times minus 390 plus 4 times minus 286 plus, well, because minus makes a plus, so plus 100. This is definitely giving a negative answer. Let's just get what this answer is. So minus 4 times, or minus 26. By the way, I'm starting from here. I'm doing this because I did 100 plus. Minus 4 times 286 minus 390 times 3. You get minus 2,214. What are we talking about? Kilojoules per mole. After all, it's still a delta H. So in kilojoules, we are working. Oh no, they just said delta H. Yeah, delta H, sorry. Delta H. We are given delta HF of these, but we're looking for delta H. So yeah, that's the answer. But if we stick to significant figures, I mean, it's kind of messed up, to be honest. So they either have this answer, or they probably have something like, I'm guessing they have something like this, times 10 to the power of 3 kilojoules. It's one of those. Anyways, it's not really important. Both of those are correct. So yeah.
Hey guys, so we'll do number 19 to 27. So let's start off with 19. So for ionization energy, you look for the biggest jump in between them. So the base jump is, this is around 2 times, and this is also around 2 times. Here it's around 2 times as well, and then another 2 times, a little more than that. And here you have more than 4 times. So this, in between this and this, is the biggest ionization energy jump. So it's group 5. Now group 5, it has 5 valence electrons, and it forms 3 minus ions. So what was the expected chloride is, you either donate all these 5 valence electrons to form a covalent bond, or you donate, it shares 3 electrons. So that's why it's either YCl3 or YCl5. The first ionization energy of aluminum is less than that of B, because valence electrons of aluminum experience more shieldings. That's right, because aluminum as you can see, is like here, the aluminum nucleus, and then you have the core, and then you have another core, and then you have these three. But boron, it just has the core, and then it has the outer shell. So there's more shielding in aluminum. As for the ionization energy of F, it's greater than O, because F has a higher nuclear charge. What this means is that this is more positive of F compared to oxygen, which is why it attracts the electrons more. The atomic radius of calcium is larger than the of Mg because it has more core electrons and more shells, which is why it's bigger, and then Mg is just this much with 2. And more shielding, obviously, because more core. The second ionization energy is greater because you have the same nuclear charge that attracts more electrons now that this is gone. So it's more focused on this electron. The atomic radius of Cl is smaller than that of S because Cl has a large nuclear charge. What this means is Cl is very small compared to S, because having a larger nuclear charge means it attracts the electrons more. Okay, so for number 21, you have these 3 photons, and you're asked what they do to molecules. So microwave, it has the least amount of energy, so all it does is just rotate the molecule. So if you have a molecule here and it just hits it, it will just maybe like rotate it, that's all. And then infrared has more energy than that. If it hits it, it will make it vibrate a lot because it has more energy. That's why it can do more damage or more effect. And then ultraviolet, it will cause electrons because since it's very energetic. You have this atom here, this is the nucleus. It will maybe cause an electron over here to move up energy levels over here because it has energy, a lot of energy, which it can use to move the electrons upwards. So that's what ultraviolet does.
Let's do number 22. The plot below shows the first ionization energies of period 3 elements. Using the plot, do you expect the following reactions? Let me just put the S. Reactions to be exothermic or endothermic. You have 2 reactions. I'll give you guys a few seconds and then we'll solve it together. Okay, let's solve it together. For the first one, I'll just be writing the half reactions of what's going on so we can visualize it better. So for the first one, we'll do Al gas plus 1 ionization energy, or ionization energy 1, to give Al plus gas plus 1 electron. Because if we refer to what I've written here, if you are removing an electron, that's endothermic, and if it's endothermic, you're absorbing energy, so it has to be on the left side, and adding electrons is exothermic. Okay, so here you can see that it is endothermic. And for the second one, Mg plus gas plus 1 electron to give Mg gas plus ionization energy 1, and this would be exothermic, right? Now if we can just compare the energies, we see that Al, if we draw the line, is approximately, let's give it a value of around 600 kilojoules. And if for the Mg, it's closer to 750. Since the value of the ionization energy of Mg is larger and it's exothermic, it makes more sense that the whole reaction would be exothermic. Think about it this way. We know that delta H for endothermic is positive, endo, and for exothermic is negative. So think of the Al height as positive and think of the whole height as negative. Which is higher? Well, obviously the negative. So the whole reaction delta H is negative for the first one. Right? Now let us go on to the second one. Okay, the second one says S gas plus Cl plus gas to give S plus gas plus Cl gas. Now we can see the quick reaction is S plus ionization energy 1 to give S plus 1 electron, and Cl plus gas plus 1 electron to give Cl gas plus 1 ionization energy, or ionization energy 1. This is endothermic or plus, and this is exothermic or minus. Now if we just quickly go back to the graph, we can see that, if I'll just erase this so it's clearer, we can see that the S here, the positive, because it was absorbing energy, and the Cl, which is higher, is negative, the whole thing. So well, this clearly shows us again that the whole reaction is negative, because the Cl energy, ionization energy of Cl, is greater than ionization energy of S, which shows us that the whole reaction delta H is negative, exothermic, and that's the answer.
Okay, so for number 23, you are asked to about the spectrometric or calorimetric method, which is basically how you determine the absorption or concentration of a solution, or the absorption of light. So you have light that goes through a hole, and then it passes through a test tube, and it has to be a colored solution. That way the light will bend in specific ways. So this is like blue, and this is red, and then you have the spectrum that measures it, the light intensity over here, and then depending on the intensity, that's how you find out the absorption or the concentration, if you know already the absorption. So let's start with the letters, the number A, B, C. So number A, it asks how do you get a concentration of such and such. This is basically just a dilution question. So for diluting the 0.1 to 0.02 using distillant 10. So you have 0.1 whatever, and then you have to dilute it to 0.02 whatever, it doesn't really matter, but the volume. But since it's 100 milliliter, it's best to just get this 100 milliliter. So CV equals CV. So 0.1, 0.02 times 100. Okay. So this is 2, this is 0.1, so this you multiply it by 20. So this is 20 milliliters. And that's A. For B, identify the optimum wavelength. It's simple, you just find the one where it's minimum or maximum here. So this is 510, 510, so this is good. And then for C, they ask what the absorption of the unknown solution is 0.275. So you just go to this graph, go to 0.275 here, down, so 0.05, which is in the range, 0.5, sorry. After this should be 0.05, there's a typing mistake. And then Beer's law, this is basically just relating the absorption, molar absorbability, path length, and concentration. So this is the jar, this is the light where it comes in, and this is it. So path length of curvette is this much, this from here to here. Molar absorbability is the molar concentration, it's how much per mole does it absorb, and then C is concentration of the solution. the solution here. And then A stands for absorbance, which is this variable. And then E, where the unknown solution leaves fingerprints. If you leave fingerprints, that means less light will go through. If less light goes through, it means that the solution absorbed it more, in a sense. If it was perfect, if it was ideal, it means that it would have absorbed it more, so the recorded absorption would be higher, which would make the concentration seem higher. So higher apparent absorption and higher reported concentration. So why is the method of determining COCl2 different than NaCl? Simple. NaCl is colorless, COCl2 is blue. So that way, since it's blue, it will reflect the light. It will reflect the light, and it doesn't go blue-red. Sorry, it actually just blocks this side and just gives out blue light. That's how light works. Okay, so for 24, they explain the photoelectron spectra. So at this energy level, there's the electron that is released, and this energy level, there's the electron that's released. So 400, why is the nitrogen less than the oxygen? Because oxygen has a greater nuclear charge of 6, while nitrogen has 5. And that's why it attracts the electrons more, because this is more positive. So oxygen has more. And as for Ne, they have to explain what is happening here. So if you write the electron configuration, it's 1s2, 2s2, 2p6. Now the height of each peak represents how many electrons. So over here you have the p orbitals, which is 6. Here you have the s orbital, which is 2. Now they're grouped together because this is the second level. And then here you have the 1s, which is really far away because it requires a lot of energy, and it's a core electron, and you have to really take it away from the nuclear charge, which is really high right now. Okay, so for number 25, this is about ionization energies. Ionization energy is just the energy to remove an electron from an atom. So the first will be to remove from the atom, the second will be to remove from the 1+ ion. So that's what they showed over here. The first, as you can see over here, this is the second. Now the second ionization energy is always larger than the first because you have the same nuclear charge, the same positive charge. So obviously if you have less electrons and now you have more positive energy devoted to attracting the electrons, that's why it's greater. Now for sodium, you have this, and then you have the shell, this is the positive nucleus, and then you have just one electron. So once you remove this, you have to remove the electron from an already stable shell. That's why it takes a lot, 9 times more. While at 1.5 only, because since this is already higher, it's only 1.5 times to remove the second one, which is in the same level. So 1.5 is relative to the one you removed last, the second one. It's really big, but it's just relative. Now, why ionization energy of sodium is less than lithium is because sodium, it has a shell protecting it, and then lithium. So this one is sodium, and then lithium is only this much. So obviously, it's more protected from this positive nucleus. Now, why ionization energy of sodium is less than magnesium? It's because Na, and then you have the shell, and then you have this and this one here. So to remove the sodium electron, you have a specific charge. But if you had the same greater charge for the same shielding and you had another electron, it would be way less because it's the same shielding. So higher nuclear charge means it's easier to remove it. It's harder to remove it, sorry. So the sodium is less. Over here, aluminum less than magnesium. Aluminum has a p electron, 11 electron in the p orbital. So to remove this, it's easier. Easier as in takes less energy. Now, why is the ionization energy of oxygen less than that of nitrogen? It's because oxygen contains 2p4. So you have this. This is for nitrogen. But for oxygen, you have the spin electron, the other spin. So since it's the same p orbital, it's actually very stable if it's half filled. So it takes less energy to remove this p. Okay, number 26, it asks about size. So Na and Na plus. Na plus just has an electron removed. So it's obviously smaller because it's less size. Cl and Cl minus. Cl has an electron added. So Cl minus is bigger. And for this, if you look in the periodic table, they all have 10 electrons. Because if you account for the ions, so it just depends on the nucleus, how big of a charge it has. So the greatest charge, which is Al, it's going to be the smallest because it will attract the electrons more closely together. And then Mg is the next, Na, then Ne, then F minus, then O2 minus, and then N3 minus, because less nuclear charge, N3 minus has less nuclear charge, so it will not attract it as much. And then for 27, you have Se and Se2 minus, and then you just write the electron configuration, its memorization, S2, S2, P, and then you have all these. So for the ion, which is 2 minus, you have to add 2 more. And then explain why the radius of Se2 minus is larger, simply because you're adding electrons to this Se atom. So obviously this one will be larger because you're adding more. But if you want to get into technical terms, adding more will increase repulsion between the existing electrons and the valence. So that's why it will just push each other more, and it will increase the average distance between the valence electrons. So the electron cloud has greater radius. For part B, the Se2 minus is isoelectronic with the Kr atom, so it has the same number of electrons. But since Se2 minus is sort of artificial in a sense, because you're adding electrons not to a natural state, it will take less energy to remove the electron from this one rather than this one. So it takes less energy for the Se2 minus, and then it requires less energy because the p orbital, and compared to this p orbital, if you compare it here, then it's artificial, as I said. And it's less attracted because the nuclear charge is smaller. And that's it. Thank you for watching.